Okay, hello. So right now we're going to continue and look at some strategies for evaluating limits algebraically. So we have some nice theorems. And again, just to remind you, I'm going to present these theorems without proof. So if you are looking for a little bit more rigor and a little bit more proof of the theorems that I present, you'll have to consult either another source for that. So we're just going to go over these techniques and these theorems without proof. So just take my word on it, I suppose. Okay. So functions that agree at all but one point. So this is a nice theorem when you have two functions that are equivalent, but maybe there's one value where they're not equivalent. And you've seen this before, and maybe you didn't realize it, but that's what we're going to kind of explore. So let's look at this example right here. Let's say I had the function f of x equals x to the third minus 1 over x minus 1. So this function, of course, hopefully you know, f of 1 is going to be undefined because you'd have 0 over 0, and that's undefined. But let's say instead of this particular function, let's say we had one that was slightly, it's similar, but let's consider, I'll change my color here a sec. Let's say I factored the x to the third minus 1 over x minus 1. So this is going to use factoring techniques. If you are getting stuck with this next step, pause the video and go watch another video. But x to the third minus 1, it actually factors to be x minus 1 times the quantity x squared plus x plus 1 all over. And then, of course, in that denominator, we have that x minus 1. So again, all I did was factor the numerator. And these functions, we're still dealing with an equivalent function. Now, if I consider, x not equaling 1, then I can actually divide out or cancel out this x minus 1. And when I do that, then I'm just left with x squared plus x plus 1. However, our function is considering x equals, x doesn't equal 1. We have a function that specifically doesn't have x equals 1. So this is actually a new function. We can call it g. And f and g are basically the same function. If you were to graph f and you were to graph g, the graphs would look the same. There'd just be one point where they're not the same, and that's specifically going to be when x equals 1. So these functions are both the same. Actually, let's pull up a graph because that might kind of better demonstrate that too for those that are visual people. So I use Desmos for graphing. But yeah, let's go ahead and look at our two functions. So the first function, we called it f, and it was equal to x to the third minus 1. And then I'm going to put parentheses all over x minus 1. All right, and then we'll have a function, we'll call it g of x, which equals x squared plus x plus 1. Okay, so again, f and g, they look to be identical graphically, but there's one slight difference. Okay, so if we look at the red graph, of course, it looks the same as g. But if I go to where x is equal to 1, right at 1, I have an open circle because we know that f is not defined when x equals 1. Versus if I go to g, and I go to 1, this is the one spot where they differ, it is defined at 1. So hopefully you agree with me. These functions agree at all but one point. And what we have then is we have a theorem that says that if two functions, and I've conveniently named them f and g, if f and g are two functions that agree at all but one point, in our specific example, they agree except for where x equals 1, then their limits are going to agree. And this works really nicely, of course, with what we know about limits. It saves us from having to graph f and consider the limits, because certainly we could graph f, do a table of values, and we would see the limit for for f, but this theorem just says actually, hey, like these are gonna have the same limits. It's in a theorem. So the limit as x minus 1, or as x approaches 1 of x to the third minus 1 over x minus 1 is going to equal the limit as x approaches 1 of x squared plus x plus 1. Now you need to be careful because you can't say that f and g are equal because they're not equal. They're very close to equal, but there's just that, again, there's that x equals 1 where they're not equal. They're not the same function. But their limits agree. So just make sure that you keep that limit notation on there, because if you take it off, then all of a sudden your functions don't agree. And now we have a polynomial and we're looking at the limit as x approaches 1 of this polynomial. So we can go ahead and substitute 1 in for that, because we know that direct substitution is possible for polynomials. We've explored that previously. So then I have 1 plus 1 plus 1, I get 3. Okay, so then we can make the conclusion the limit as x approaches 1 of x to the third minus 1 over x minus 1 equals 3, because we found an equivalent function that agrees at all but one point. So, all right. Thank you, and yeah, hope you enjoyed this video.